So welcome back to our listeners. Thanks for listening. We got a special guest, Ruben Moser, on.
Howdy.
We're excited to have Rube on. Talk some a little more in-depth topics, but nothing that our listeners can't handle, I'm sure.
Our listeners are some of the most intelligent people out there.
Yeah, we have full confidence that our listeners will understand every single word. So, yep. But yeah, so I don't know. Hudson's got the topics all laid out here. I don't know if we want to dive right in, or maybe you could give a little bit about some of your interests and kind of where you're at to give a background.
Yeah,
for
well, as you can see, we have a lot of math and physics topics. I am currently in grad school going for a mathematics PhD.
Nice.
And did my undergrad, had it in math and physics, so I have a background there, and so that's
nice.
Brief idea.
Where are you currently studying? Or is that what it's still called?
Well, I'm studying math. I will have a specialty later on.
But like,
right
what
now.
school are you at?
Oh, at Purdue.
Oh, okay. Just for our listeners, they might not have known.
So you graduated 4 years ago? 5 years ago?
Graduated high school?
Yeah, high school.
Oh.
So I'm saying, what year of college are you in here?
Yeah, this would be like year 5.
Year 5, okay.
Something
Nice.
like that, yeah.
So you'd say you definitely would you say you enjoy it, or would you say you're just ready to be kind of on to the next thing afterwards? Like, do you find yourself enjoying to learn? I would assume.
Yeah. Yeah, there's moments of, you wish you could move on, but I like studying and like learning, so.
That's good.
You've got to the point where you can like be what's not the student teacher, the GA, what are those called?
TA?
TA maybe.
Teacher's assistant?
Teaching assistant, yeah. Yeah.
I was like, GA, Georgia?
Anyway, and GT, or I don't know what they call them. Are you that now? Is this what you do?
Yeah.
Okay.
So that's kind of like tutoring, kind of, or is it like a?
Well, it's like teaching. It's not teaching a class per se, but it's more like a review session where you go over problems with the class. So like they'll have a lecture that maybe lectures, I don't know, 100, 200 students, say in a calc class. And then you have much smaller, like maybe 20 student sections where you have then a grad student that
Just break down classes, kind of.
yeah, like to review problems with them or like do quizzes or something. So
Graduate assistant. I think that's what they call him, because he'd grade all of our projects, so we'd have to meet with him and talk about the stuff we did.
yeah, I mean that would be the same thing. Teaching assistant, graduate assistant.
Okay.
Yeah.
I've never heard of a graduate assistant.
I thought that's what I'm almost positive we said GA. Anyway, it doesn't
I don't
matter.
know.
The
only
point
one that
is
says
the
in
point
college,
is it's a
so-
smarter student that helps us. I think that's what the point. So do you enjoy that? Like, do you enjoy? I don't know how much student interaction you get, but do you enjoy this?
Yeah,
It's all right.
Yeah.
Pays the bills.
it does.
Yeah. There you go.
Nice.
Dude, I've been wondering about this. Was math invented or was math discovered?
Should we go around and say all of our first opinions?
Yeah.
Let's say the
Seth,
best.
start us. Ruben will end it.
I think the science probably was discovered, but I think the framework of mathematics is like there's going to be two objects here. So if you call the number 2, the symbols and all that was probably invented, but I think we could have made different symbols or whatever, but there would have been some counting or whatever math really is kind of, it just is. But I think how we interpret it, we invented our interpretation of it, and then we call that math. So I think kind of a both, but I would say the word mathematics and all the plus and the minus and all the symbols and all that, I think is invented, but I think like counting is kind of just a truth or a absolute.
So you would say math was discovered.
I was gonna say, which one are you closer to if you had to pick one or the
Math
other?
is invented or discovered. I would say Oh man, no, I'd say invented. It seems like Yeah, I'll say invented.
Well, okay. Bert, do we have internet?
Yeah. No.
Oh, okay, that's
yeah,
fine.
we do.
Well, just look up the definition of math, because we say it all the
Yeah,
time.
that might.
I really think that,
That
we
would
need
be
to
helpful.
know exactly what we're dealing with as far as the definition. Because I think that kind of entwined into it a little bit is language in general. Like, we came up with a word for two objects being two, right? We came up with a symbol for that.
All that I think is invented, but the
Yeah.
actual.
But I mean, when God created the earth, He created a number of things, which is, if a number is considered math, you know, I guess I don't really. The systematic study of numbers. Okay, shapes.
Quantities and patterns, often described as the language of logic, provides a foundational framework and tools used to model reality, solve problems, and analyze structures in science, technology, and daily life.
Well, if it's a study, then one would think that it would be invented.
Okay, so you're on the invented side as well.
I don't know. I don't know for sure. What'd you decide
I'll
on?
just pick one.
Eeny, meeny, miny, mo. Invented.
Yeah, I think the study and all that, it's invented, but there's like an aspect of it that we're discovering. But the tools that we use to discover, we invented, and we call that math.
Okay. I feel like I'm gonna be on whatever side Ruben is after he says.
Yeah,
But
I agree. The I've always thought, isn't mathematics like considered like the language of science?
Language of logic, yeah.
Or yeah, I've always heard language of
I
science.
mean, I think it's
Probably so.
is it. I think called the Queen of the Sciences or something. I mean, it is a sort of a language for the sciences, but
Sure. And like science, I don't think was really I don't think that was really invented. I think that was discovered. And so if math is the language of science, I think that would also be discovered. This is kind of how my brain. I didn't think about this very much, but I don't know. I would kind of be on the discovered side. So now give us the answer, Ruben.
Wait, what was Isaac? I forget what you
I
were.
forget too. Invented.
Invented.
Or yeah, sure. We'll just go invented.
I can give you my opinion, but I don't think there's a definite answer. But yeah, I would lean more towards the invented side because there's definitely, so similar to maybe Seth, there's definitely aspects of reality that, I mean, follow patterns, follow laws.
We lost the camera. I'm sorry. Real fast. We should probably get this figured out. You get it?
I
Did it
started.
die? Did your phone die? Was it low?
I started a new one. It was just your phone just went black. It didn't die though.
Is it good how we
We're
are?
good now.
It's fine.
But your new
I'm
one
sorry to
probably
interrupt.
wasn't
Ruben.
Wait, hold up.
We'll figure it out.
Okay.
The reason he does that is to synchronize all the audio and the video.
Anyway, where were we?
Yes.
We might have a little black segment for our audio, for our visual watchers.
Technical difficulties.
But it'll be good.
So, I mean, I definitely believe there's, say, laws that physical reality follows or corresponds to. And so math is very useful in describing that. But at the same time, we can develop ideas and concepts in math that don't have any correspondence to physical reality at all. So I think that like once you kind of develop the tools, there's maybe some fixed you can't just like, if you have, say, the primes, are you familiar with the primes?
Somewhat,
Yeah. Like we can't just once we have the definition of a prime number, we can't just declare any number a prime number. It has to
follow our rules.
Has to follow our rules.
Yeah.
But we can come up with any definition or like system we want to. Some systems would be kind of useless or pointless, so we definitely like our systems to have use. And
Does this apply to like discrete and set theory? I don't feel like you could. I feel like this is stuff that we talk about in that course. It was like you can make a set of anything, but some.
I mean, a prime number is something that can't be divided, right? Or like that can't be.
It has, Yeah, the only numbers that divide into, or natural numbers, whole numbers that
Right.
divide into it are 1 in itself. So like,
So like 3, 7, 5.
yeah,
Sure.
yeah. So we can't just go and say, once we have that definition of prime, we can't say 4 is prime. I mean, 2 divides it and 1 divides it.
So you're saying whoever came up with that definition invented it. So are you going towards the side of invented towards certain concepts? Like there's concepts in math that are invented is kind of what you're going towards.
Yeah, but also we sometimes have those concepts that come from reality, like say counting is a very basic idea. So we can define a rigorous system of how the natural numbers work, the counting numbers work. But we want our system to behave like objects normally would. If you have 2 objects and you add 2 more objects, you want to get 4 objects out. You could design a system that doesn't follow that, but it wouldn't be very useful.
So if you took this into another field, like mammals, it's a definition that we invented, but the actual animals we discovered. So it's like we could have came up with something other than a mammal. Like let's just say everything that's green is called John Deere or something, and it belongs in this one group, and everything that swims is called
Different
fish.
classifications.
Right.
So
Yeah.
it's all the same. It's all just language.
I would say it's not necessarily just semantics, the language, because we could, for example, come up with a new type of animal that doesn't exist in reality. We could say there could be flying unicorns, and there would be presumably no biological laws against flying unicorns. That doesn't mean they exist. So in the same way, we can have mathematical systems that we come up with that don't have any like correspondence to reality.
Ooh.
So, back to like counting or like prime numbers. Like I mean, like this is very basic, but like if you have if you have 5 apples, I mean you can't divide that like evenly without cutting in half.
Yeah.
So I mean that like defies like the real world. Whereas if you had like 6, you could obviously do 3 and 3. Is that kind of what you're saying? Like I mean, there's some just like truths that are just inherent.
Well, there's some. I mean, yeah, there's some logical restrictions we can't go past. I mean, once you define your rules you're playing with, or like axioms as you would hear in math.
Yep.
Then once you set those, then you're fixed to whatever logical results follow. But we do have flexibility in the systems like the axioms we start with, or even like the logical rules we use. Like you can. I'm trying to think of a good example. Like, say something is like Ike, for example. He is either bald or he's not bald. Okay?
Yep.
That's a standard law of logic.
It's a one
true,
or the other.
It's one or the other.
True or false.
But you could actually define logical systems that don't necessarily follow that. That could have, like, say a 3-valued logic, like he's bald and not bald at the same time, and that wouldn't have, like, say physical meaning, but there's no restriction of why we can't define a system like that and play around with it. We don't normally use logical systems like that because they have less use to us. We in general
they're
like
not as logical, or not as practical.
They're not as practical, but mathematicians often don't necessarily care about the practical side. A lot do, but
Right.
Yeah.
Okay.
All this to say, you think math's invented, if you had to boil it down?
I would be closer to the invented side. There's definitely things that seem discovered about it, so it's not a clear-cut answer, but I would
Right.
lean towards the the
I mean,
invented side.
One of the things that, or like one of the aspects that would seem, in my opinion, to be like have been discovered is like the theory of relativity or something like that. Like that seems like it was something that was discovered. You know what I mean? Would I be right about that? Or I guess I don't know very much about the theory of relativity.
I would more agree with that because there you're talking about something that's corresponding to reality. You're describing reality. So
Sure.
But how did he found that with math, if I'm not wrong on that. Like he came out with equations and like it wasn't just observed through a telescope like Galileo did when he saw moons or something.
Well,
It's like
there's definitely, with physics, there's definitely observational evidence, and that does, like, we have evidence, we have observations, and then we want a model that fits that.
mm-hmm.
So there was definitely, like, physical things that
He might not have done the research, but he was building off of work of people that had.
yeah, and you were saying it also is very mathematical. Like, if you have these observations and then you design this mathematical system that fits those observations, it also then we can do more math with it, and wherever what the math says, we can expect then our physical reality to follow what the math predicts.
Right.
Which
Which was this like black holes, white holes kind of a deal? Like, is this kind of like didn't he have some equation and it was like kind of thought impossible because at some point it met a singularity and then they're like, oh, there can't be singularities.
well, yeah, okay. So when
He is Albert Einstein, right?
Albert Einstein, yep. So he released kind of two types of relativity: a special relativity first, and then a more general relativity later.
Well, like briefly, in one or two sentences, can you like explain the difference between the two, or are they not?
We gotta go into them. It will be
Oh,
more than two
okay,
sentences.
that's fine.
We'll go back to that in just a second if you want. Anyway, when he released his several papers on general relativity, different mathematician Schwarzschild,
Mm-hmm.
several months later, he found a solution to it, which was effectively a mathematical solution for a black hole, which does have a point of singularity where it predicts that you'll have an infinite density of mass in a point.
Mm-hmm.
So you wouldn't think intuitively that reality corresponds to that. So actually Einstein didn't like that it could generate black holes. So he wanted to show that they were impossible, but we have good observational evidence that something like a black hole does exist.
So he actually worked against his theory to try to find which I guess that's a sign of
Proving it out.
So he inadvertently proved that they existed and then was working to attempt to disprove his own theory.
Well, this also, his theory predicted that they could exist, like that a black hole would satisfy his equations. That doesn't mean they do exist. There could be some other reason why they're prevented from forming in the first place.
Okay, so he didn't necessarily prove them.
He didn't prove they exist, but he proved that the model he came up with didn't have any conflict with them, and he wanted to find a reason why there couldn't be.
Okay.
Can you give, or maybe it'd be easier to just look up Google's definition on just the theory of relativity overall? Because you're saying that there's situational. What was the two you were saying? There's two.
Special and general.
Special and general. Maybe if we just got a brief overview.
All right. Einstein's theory of relativity consists of two groundbreaking frameworks: special relativity, which he discovered in 1905.
That's insane.
That explains the connection between space, time, and speed. And then general relativity, he discovered in 1915, that redefined our understanding of gravity. Okay, that's interesting because whenever I think of the theory of relativity, I kind of just associate that with gravity. Like I didn't realize that there was two different theories, I guess.
Well, yeah, his special relativity didn't really deal with gravity. But you've heard of the concept of space time?
Yes, yeah.
So that idea was more or less introduced with special relativity, where we treat time as another dimension along with our three spatial dimensions.
Yep, it was the fourth dimension.
It's a fourth dimension. So, instead of having our three spatial dimensions, we have time is treated in the same framework as spatial dimensions in a four-dimensional space. Which is kind of wild.
That is wild.
It's just insanely wild. You can't picture fourth dimensional space, right?
I will tell you, trying to study special relativity at all is so.
I bet it was even more wild for the people at that time to all of a sudden be like,
Yeah, we've had over a
100
is it a
years.
century? At
like
this
I mean
point?
we've
To
all
think on
watched
this.
movies dealing with concepts like time travel and just such, but like to people at that time that must have been such a foreign concept where they just like, what?
Yeah, I think that's one reason why he was successful or considered like a genius eventually, at least, is he was maybe willing to. Once he had some basic ideas that he knew he wanted to follow, and so once he had those, he just allowed whatever the results followed from that and just allowed those. So like if it needed a framework that had time as a fourth dimension, he developed that and used that. I mean, wasn't necessarily immediately opposed to that.
Okay. So he was willing to investigate, willing to like, I don't know, like dig into different ideas that he didn't necessarily believe.
Or that would maybe at first, with special relativity, he started with two ideas that maybe that are more natural but lead to unnatural results. But if he wanted to accept his two principles, say, which we can get to, then the conclusion that followed he needed to accept, and he was willing to do that. So like his special relativity kind of was built on two principles. One is the idea that physics is the same for any different observer. So like when I'm in this location over here, I can do an experiment and I should expect the same results if Ike does the same experiments over there or at a different time.
Okay.
Or if he's, say, moving through space or something.
Okay, so you can expect the same results of doing an experiment right here on ground at 8 p.m. versus Ike in an airplane at 6 a.m. or something.
Yeah, with some technicalities with the movement,
the airplane, sure.
But
And is this what he found to be true, or is that where he started and found something else?
well, that's one of his basic ideas or principles that he was trying to base his theory on. So he wanted that to hold. He thought that would hold, and that's a logical thing to expect. The other idea that is needed for special relativity is the idea that this is actually kind of unintuitive. Is that the speed of light is the same for any observer. So
was there a speed of light constant before this time?
there was a speed of light constant, and like have you heard of like Maxwell's equations?
Yeah.
They're used to describe light, and they're the kind of theory of magnetism and light and electricity. So those had were being developed around the same time, and they suggest that the speed of light is constant. So there was observational evidence that the speed of light was constant, or people thought at one point there might be an ether. Have you ever heard of ether theories?
I have not heard of either.
What's an ether theory?
So like
This is people around that same time that he was.
same time, yeah. Like say we have it's a theory of waves. So like in an ocean we have waves in water. We have the waves propagating through water.
Yeah.
So we have the idea that light is a wave, and people said, okay, if light's a wave, what's it propagating through? Like what medium, what material is...
Waves propagate through water. What is light propagate?
Yeah, or
Well-
like sound waves need air to travel. Like if you're in a vacuum in space, you
Because
can't...
you're saying light can travel through air and water, and
light
nothing.
Can
And
travel
nothing,
through a vacuum.
yeah.
It can travel through nothing. But
so you're trying to
people,
find a constant thing that it travels through.
yeah, people thought, oh, there might be this ether that is very hard to detect that light is traveling through. So when we think there's a vacuum, it's actually not a vacuum. It has this ether.
Hmm.
So
And this is an old theory, like Isaac said. This isn't something people are thinking now. This is like in Einstein's
oh, this
time.
is definitely disproven.
Okay.
This is
Okay.
So you can do experiments to test if that's true. Like say, go back to an ocean. If you have a current,
Yep.
or something. If you say have a sailboat moving in one direction at a certain speed, say going against the current, it will slow down. Versus if you're going with the current, it will speed up.
Mhm.
So if you have the Earth that's moving through this ether, as it orbits the sun, it's changing directions. So you would expect that
Like a shift in color or something.
you would
with it.
expect that your light changes speed depending on which direction it's
That makes sense.
Oh, I
it's
see.
yeah.
Okay.
and various physicists did experiments and didn't see any evidence that it did change any speed. So that was
So would that look like colors just slightly shifting a little bit because the wavelength would change, or the speed would change, therefore changing the wavelength? Is that like what would they have expected to see in these experiments for that?
well, yeah, you would need a change in speed. So would they have expected a change in frequency? I'm not exactly sure what
Like
effects they
a
would
somehow they were
do,
doing
but
some
yeah.
A
kind of-
Doppler
to try to
effect
figure
for
it out.
light.
Yeah, it would
Yeah.
be related to a Doppler effect.
Which we do observe Doppler effects for lights, right? With stars or something. Aren't they red shifted or blue shifted or?
What's a Doppler effect?
Yeah, well, that's different. That is true.
Wait, on his question, Doppler effects, like if a car is driving past you with the horn on.
Hold up, we just pulled it up.
How the pitch.
It's the change in its observed frequency and wavelength caused by the relative motion between the light source and the observer. Okay, so what were you saying?
Like when like an ambulance drives by, like when it's like really kind of high pitched, and once you passes you, then it goes.
Oh, sure, yeah.
Like that kind of whole idea of
Yeah.
movement is because like as it's moving, the waves are pushed together because of its motion, and then once it's
Gotcha.
passed, they get
Okay,
stretched
yeah,
out
yeah,
relative to you, and it's moving.
I can picture that. Yep. And kind of like
So-
a bell curve, but of the.
Yeah.
So the same could work with light, but it just has to be way faster, right? Essentially.
I thought it was something like that. Like they could tell a red shifted star or something.
Like, I mean,
Yeah,
that's
there's multiple concepts at play.
Light waves travel through a vacuum because the speed of light is constant. Relative motion changes the wavelength and frequency instead of the speed. Blue shift moving towards. When a light source moves towards an observer, the light waves are compressed. This shortens the wavelength, increasing. Okay, that's kind of intuitive. Way everyday cosmic. Well, you might not notice the Doppler shift when with your own eyes. In everyday life, it is a crucial tool in modern science.
Hmm.
Speeding tickets. Police radars use the Doppler effect with radio waves. Oh, that's cool. Back off
Well,
the Oh, that makes
The
sense.
I guess, I mean, that
the
makes sense.
speed isn't
Yeah.
changing. You can also get a Doppler effect.
Right, it's not the speed, it's the frequency, which is not related to speed, I believe. I don't know. Anyway,
Oh, well,
I should be arguing.
The speed is related to both the frequency and the wavelength.
Oh, okay.
So you could change the frequency and also change the wavelength without changing the speed.
But they would both have to change.
They would both have to change.
Gotcha.
So light always moves at the same speed. Like that was proven.
Well, proven, quote unquote. I mean,
Okay.
nothing's ever really proven. I mean, in physics, you always have possible error, and
Sure, but it's okay.
evidence to suggest that.
Okay,
And-
that's the terms that they would use. There's evidence to suggest. That's how they would say it.
I'm not sure if they would use that exactly, but they wouldn't say it's proven. They
Okay.
definitely wouldn't say it's proven.
Okay. There's a strong likelihood
It's just a
of.
theory until it's proven, right? Technically.
Well,
So
it's
everything is-
always a theory.
So
It's
everything
not-
is always a theory if nothing is ever proven.
in
pretty
some
hard to
sense,
know,
yeah. I mean,
Yeah.
So with relativity, this kind of brought up the discussion of like time travel too. If you move, like I know, like in like middle school or something, you always tell me how like if you went by a black hole and came back, it would be 1,000,000 years later, but to you it'd only be like 1,000 years, and it's like what?
so
Or go back in time. I don't know if you can go back in time. Anyway,
yes, so both special relativity and general relativity predicts what would be known as time dilation.
okay, not actual travel.
Which, okay, depending on your idea of time travel, some people would describe it as time travel and some wouldn't.
I think that what most people would think time travel is that you can move forward in someone else's timeline.
Hey, Bert, could you pull it up? What is time travel?
I mean, traveling in time.
Well,
I mean, I think of like.
most people would say
Like,
you
if I can go to
travel
Isaac's-
backwards in time.
Mhm.
So you want to
Have you seen the Avengers?
no.
Okay, I was gonna say.
It's interesting to me how like every movie portrays time travel in a different way.
Yeah, but whenever I think of it, I think of.
Okay, so I mean,
Okay.
according to Google, time travel is the hypothetical or theoretical concept of moving forward or backwards through different points in time.
See, they allow for forward in time, which is the type of time travel that's definitely observed with relativity.
Mm-hmm.
Wait, what do you mean observed? It's happened?
So, yeah, we definitely observe a sort of time travel to the future. So, for example, you were saying, if you go to a black hole or something,
Mm-hmm.
you don't even need that. So,
I just need the moon.
if you
The Artemis astronauts are actually 5 days in the future.
Ooh.
with special relativity, you might hear the term like moving clocks run slower. So if say I'm floating in space and you're floating in space
Okay.
side by side, and we're both at rest to one another, okay, that's all good. We both have a watch on. I look at my watch, it's ticking at a certain rate. I look at your watch, it's ticking at the same rate.
Okay.
We're all good.
Okay.
Now, let's say you start to move. Now you're moving. You say go back a while and then accelerate, and now you whiz by me. You go by me real fast, and I
Okay.
look at your watch while you go by. I will look at your watch and see it moving slower. So from my perspective, the rate at which you're experiencing time has slowed down.
Okay. What about it from my perspective?
But from your perspective, your watch still seems normal. Always from your own perspective, your watch.
From his perspective, how does he view you?
So since from his perspective, if he moves by me, it's equivalent to me moving by him. That's kind of a relative. It's like if you're on a train and you're looking out a window, sometimes it's hard to tell if you're the train moving or
Yeah.
if the
The
other
land's
train's
moving.
moving.
So you would
Yeah.
each view each other as the same and your own the same.
Well, so if from his perspective, would he view you as yours moving faster? Would it be reversed?
Yeah, it would be reversed.
That's interesting.
Anyway, so you can theoretically take advantage of this.
Okay.
You would have to be moving really, really quickly.
Right. Like faster than we've been able to go.
As humans,
Yeah.
But if I wanted to, like, if you wanted to say go into my future, say you wanted to see me get old and die, okay?
Seth is a freak like that.
So you could get on a rocket ship, get near to the speed of light, do a little trip, and come back. So do you maybe went on a 10-year trip.
Okay.
But if you're going fast enough, I gotta make sure I have the times correct. But you would come back, and I would have.
My time would have moved slower while I was moving. Your time would have kept moving, in essence, faster. So while the whole time I'm moving,
Yeah,
my time
yep.
kind of slows down, and yours continues
Well,
normally.
from your perspective, he slows down.
From his
Yeah, so
perspective.
that would mean you would
and
get
from
one,
my
really.
perspective,
From your
his would speed up, but
Right.
I don't know
Oh,
if
yeah.
I could
So
see
for
that.
for what Seth feels like, or like was 10 years, or felt like 10 years, whenever he comes back, you would have aged more than 10 years.
Yeah.
His
yeah.
time would have sped up, and my 10 years would have slowed down to him and become 100.
Right, but from his perspective, you've been gone for 80 years or something.
Whatever.
Yeah. So I still experienced that full, 80 years like normal.
So
And
this
he experienced the normal 10 years, but once we come back together, now we're back to the same rate of time, but
So you're saying it's a true fact that if the amount of speed a human could travel physically was not a question, if you could just instantly travel the speed of light, then
or near the speed.
or
of
near
light.
near the speed of light, if that wasn't the issue, if you could do that, then it is actually possible to time travel. So the only reason holding us back is we can't move that fast.
Well, in the sense of that sort of time travel where you're
Going to the future.
Right.
you're basically getting to a future event quicker than you normally would, even though you still.
Which is like, why would you want to do that? That's not very practical, I feel like.
I mean, I guess if you
Yeah.
thought the Earth was going to nuke itself and you wanted to come back in 10,000 years, maybe that would be nice.
And get the radiation sickness.
Yeah, or something. Anyway, so we can't move fast enough.
Because a thing with mass cannot move the speed of light, and a thing that doesn't have mass can't move slower than the speed of light, something like that.
I would.
Deep.
I think of Brian Cox or something said something like that. Like
Yeah.
light cannot move slower than the speed of light, and something that has mass cannot be like we can get close, but we can't actually.
Yeah, we can't.
Yeah.
But you said we don't need to move exactly at the speed of light.
No. Even if it's moving, even if he's moving at 5 miles per hour, we would experience a slight different rate of change in our
Okay.
time.
Okay. So what? So
It
you're
would
saying
be
if
undetectable.
somebody lived their entire life, okay, so if there's two different spaceships, right? One spaceship is moving 100 miles an hour faster or something through space. Over the length of 100 years of someone's whole life, they might have aged an extra few days faster. That's kind of what you're saying.
It would
That's
not
so
be
incremental.
It would not be a few days. It would be much smaller than
Really?
that.
So it could be seconds.
Unless you're moving, you have to be moving
really
really
a
fast.
lot faster.
There's also time dilation caused by being near like a black hole, large gravitational pull.
Like the whole premise of Interstellar, pretty much.
Yeah.
Yeah.
Well, even just what we were
That's-
talking about
that's
is
general
Interstellar.
relativity.
Like whenever he went to
Right.
that one planet, that's literally
But
Interstellar.
that was because of gravity. That's what he's talking about.
Yeah. So it's
gravity's was making him move that fast.
so you could be moving faster or you can be in a gravitational field. Like The
Okay.
more
Yeah, okay.
gravitational pull you're experiencing,
Okay, yeah, no, dive into it.
you also you'll experience time dilation. So like in Interstellar, when they went to the
Miller's planet.
massive planet where the gravitation was much stronger, they were also, their clocks again were running normal for them, but relative to the people in the spacecraft, which were not in that strong gravitational field, the people in the gravitational field, it appears their clocks are moving slower.
Mm-hmm.
Is this something that is thought to be true as the same way that traveling
Well-
at fast speeds?
Yeah, it's thought to be true, and we definitely have observational evidence that
Okay,
it is
okay.
true. For example, GPS 100% requires, like we have relativistic calculations correcting the error in GPS signals. So like GPS requires very precise timing of satellite. Like we have a receiver on Earth and we need to know the time to say multiple satellites. So like satellite A, satellite B, satellite C, we get a certain time, we send a signal out and it sends it back, so we get a
distance.
distance.
Yep.
Basically. We're using time to get distance basically. And you can do that with multiple satellites, and so you can get your location accurately. So that requires accurate timing. But those satellites are both moving faster than we are, and they experience slightly less gravity than we
Sure.
do, since
Yep.
they're farther from the Earth's center.
Mm-hmm.
So both of those effects make the clocks run at slightly different rates. So I forget if it's like, I don't know if it's like 40 microseconds per day or something. I don't know.
Okay. Very, very minuscule.
But you're at already your scale is minuscule because you're measuring time of like the
But you
transmission.
need to be you need a high level of accuracy if you want to have your.
So that little bit off would make your GPS pretty much worthless if it wasn't accounted, at least to the precision.
And it's also that the errors accumulate over time.
So your
So
location
you could
would
maybe
drift.
deal with it. You could maybe deal with it for a day or a week or something.
Well, this is because of the gravity or because of their speed that they get 40 microseconds or whatever off.
It's a combination of both. They both affect it.
Okay.
I think the gravitational effect is higher than the speed difference, but I don't know which one it's
Because
more
the
significant.
satellite's moving, you know. you
Right.
see
So
it-
that's why to me that seems like a speed thing, not.
But then it's
gravity.
also
they
farther
actually
from Earth.
one cancels the, like
one
the sat-
helps out and one.
the satellite's moving quicker, so it to us it's moving slower, but it's also. I got see all these things you got.
But also we are closer to
Yeah.
the gravity source, so it's
so
time
we're
to
also
us
moving
also.
slower, quote
I got-
unquote.
yeah.
So yeah.
Yeah.
So we're like Cooper on the planet, and the satellites are like the other
the
dude in the
spacecraft,
ship. So
yeah.
for us, his time's moving fast, but also they're moving fast, so and they cancel out.
So I'm having a hard time thinking of how like this black hole with the gravity can result in time travel. Or yeah. Can you explain that?
So it's because it's like stretches the space time effectively, or curves space time. If you've heard of curving space time,
No, I've not.
This is also something proven to be or visualized to be true, or just thought to be true.
Like accretion,
Actually,
they
you're saying physically bending space, and which is essentially kind of a black hole, right?
well,
Like this is all physical.
any matter, according to the theory of relativity,
Mhm.
if you believe what it says, and it does predict a lot of things that follows reality, I can get into even more observational evidence for relativity. So there's a lot of things it predicts. So if you're going based off of what the theory says, then we have this 4D space-time. that mass curves, which a common analogy for this is say you have, say like a trampoline.
Yep.
So this is going to be, say, like a two-dimensional space-time where one dimension is your spatial dimension. So you only have one spatial dimension now.
Okay.
And then your other dimension is your time. So it's still hard to comprehend.
It is.
Because we're not used to time as a dimension. And say you put like a bowling ball on the trampoline. That bowling ball, say, depresses the trampoline, which is, the analogy loses some of its power because you're relying on gravity of the bowling ball to pull down the trampoline, so you're using gravity to explain gravity. But so you get a curvature on the surface of the trampoline.
Yep.
So say I have the trampoline and I have the bowling ball on it, and it depresses the trampoline into, say, the hemisphere, half of a sphere.
Okay.
So to demonstrate how you can have like weird effects arise. So you have two people then that are like on the equator of that hemisphere, and they're moving straight north.
Okay.
So if it was just a flat plane, they move straight north, both of them moving straight north, they're going to stay parallel to each other and never meet.
Right. Yep.
But if you have it curved now, so it's now like on a hemisphere, move straight north, as you get closer to the North Pole,
They'll meet.
they'll meet. So even though they're both still going in a straight line, their distance is actually
Decreasing.
decreasing. So you get,
Well, that's because the north, what you're describing as north, has changed, right? In that situation.
They're both the people are going.
In
what
this
they observe.
trampoline bowling ball analogy, where is north in this on this?
It's relative to the person.
it's just
right?
wherever, say like you have the flat plane and you pinch it in a point and you lift up the trampoline so
yep.
it forms the hemisphere. So it's that pinnacle point where the
Okay.
North Pole
Yeah,
would
I
be.
see. Okay.
Yeah.
I see.
But the thing is, they're still both going straight. Like, you could choose any two parallel straight lines on a flat plane, they'll never meet.
Mm-hmm.
So it's only because you're curving it that you get the distance to decrease. And so if you imagine that one of the, like, say, heading towards the North Pole, say, is your time dimension. As they experience time, the objects will naturally, say, be attracted to each other.
Okay. They'll draw closer
Because
together.
the distance is decreasing. So that's like your gravity is arising because of the curvature.
Okay. And the curvature is the gravity, or is caused by the gravity.
The curvature is caused by the presence of mass.
Okay.
So there's a kind of a famous phrase where in general relativity where the mass causes or tells space-time how to curve, and like the curvature of space-time then tells the mass how to move. So the presence of mass curves the space-time, but the curvature of the space-time dictates how that object is then going to move.
Okay.
But the thing is, that object is following some line in your space-time, but since space-time is like one coherent four-dimensional object, your object doesn't have to just go straight along like
I think you're passing us, Rube.
Okay.
Yeah, it
Let me
didn't
try to-
quite.
So at bowling ball trampoline, if you're at two different points on, so this would be like the interstellar thing, to where the right Cooper, whenever they're on the planet, they're closer to
The black hole.
yeah, they're at a different space time to where it's like you're saying it's stretched to where okay, it kind of is a little bit making sense in my head to where they're just because they're at different places, time in that area just is moving faster because it's bent less or more.
yeah, like because the space, it's all of space time that's being curved. So in this situation we're describing where the objects were getting closer as they move, they're attracted to each other, but it's space time, so the time dimension can be stretched and curved as well.
If you're closer to the mass, then the time like is more warped.
Yes, it's there's more warp, there's more curvature near the mass.
Okay,
and
yeah,
therefore
yeah.
more time curvature too, which would apply to time travel. Okay.
Yes.
Okay.
So,
Feasible.
so it would be. So theoretically, someone could show up any day in an Apollo-like rocket. No, because then we would have had them in history of them launching. I was going to say somebody could show up maybe in 100 years. Let's say we launch somebody, and then they go in their spaceship, and then they go around maybe the sun. They can get fast enough and close enough to the sun and come back. Then on Earth, they'll come back, and maybe our technology will have advanced forever, like 1,000 years. But then they're going to come back in some, like, Apollo 11 looking rocket, and we're like, yeah, this is what we space traveled in. And,
Yes,
like
exactly.
that, or somebody could come back from before our time history. Maybe there was a wipe or something. This is kind of breaks down with
GTA
Christian.
6 still won't be out when he comes back, by the way.
Yeah, that would be an interesting movie, actually.
So because humanity is nowhere close to moving near the speed of light, it's impossible for that sort of time travel to ever have happened, right?
Yeah, correct.
So then the alternative method with the black holes and the gravity, could that possibly have been achieved?
Well, you would have to get close to a black hole, for example.
So I guess where's the nearest black hole?
Center of our Milky Way.
I was going to say, I think they believe there's one in the center of our Milky Way, which is going to be very far.
Okay, and so I mean, realistically,
and to get there in a reasonable amount of time, you would already want to speed up to close to the speed of light to get there in a reasonable
And if
time.
you can do that,
right?
then
Because we've not been to space, or I mean, the first time we got to space
Like,
was the '60s.
The closest star takes, say, over 2 years for light to travel there.
that's
Okay,
crazy.
right.
And
So even if you could
think of
travel,
I don't know, millions, billions of stars in the Milky Way. So if you try to get to the center of all that, you're going
And we've
thousands
already,
of
and we've
light
already
years away.
determined that we can't move near the speed of light, and so what you're saying is time travel. There's no way that time travel has happened yet.
It happens. It's just it's
Very
not
minute.
significant.
Or I guess there's no way that humanity has time traveled yet.
in a significant manner, unless there's some hidden wipeout of knowledge or something. Yes.
Okay.
Which
what
I don't
about
believe.
That goes against
so
our
that's
Christianity.
all. You could never get. There's no in any of this way you could go back in time, is there?
Well, this is where it gets interesting.
I think this whole thing's been pretty interesting.
Agreed.
So, this is again where you could theoretically have like loops in your space-time.
Wormholes.
Would be considered a wormhole, yes. Where the theory, the math itself doesn't, like, they could theoretically exist. Where, say, like a two-dimensional analogy would be like if you had a, say, sheet of paper and you fold it over on itself, and then you can, the 2 points of the sheet are real close together, and you could form like a tunnel between them.
Mm-hmm.
And so the object moving between them moved a little bit of distance, didn't have to move far, but the equivalent distance around the sheet of paper then is large. So you could like the framework of relativity, the math itself doesn't disallow those as existing, but there's no known mechanism for, say, generating one. Like, there's no known idea of why they would exist anyway, and even if they would exist,
We could never
if they-
access it, kind of.
yeah. Well, there's just a billion different theories here because like there's so many like what's the word?
Cataclysmic.
No.
Catastrophic.
What's
Causality or something. Like I never remember. Causality, yes. Causality, thank you.
So something with cause.
Like the grandfather paradox, where if you would go back in time and kill your grandfather,
Will you still be alive?
would you still be alive? So there's
Yeah.
But those are all issues with time, with what happened to reality if you could go back in the past. But they're not
Well,
actually like
but that's
preventing
and
you.
very
again,
good
it's-
evidence
it's-
that we could
we're
never.
kind of back to the idea where these are mathematical descriptions that you can follow, but that doesn't mean they're the actual descriptions of reality. Like we do have a lot of things that are predicted by general relativity and special relativity.
Well, I mean, black holes are. When
That-
Einstein predicted black holes, we didn't know any existed, but it mathematically made sense. And then eventually we think we discovered them, and now they do exist. So what would be blocking us from? Because that didn't make sense in our current reality that you could pass a point of singularity, and then never return.
Well, we don't know what happens to physics at the singularity.
Right, but that's its own question.
And like, in my perspective, I don't believe that those, say, like loops in space time could exist. Like maybe general relativity allows for it, but then I don't think that that's actually what reality is. Like, so I don't think general relativity is the exact description of reality.
Like there could be a better theory that comes along though.
Yeah, there would be
Yeah.
better theories. Like, and we don't even like with the black holes, we don't know how they behave like at the singularity.
Which it can be. We can predict it we can predict it following the equation down, but we don't actually know what that would do
Well,
to
we
reality.
don't even know what it does at the singularity. Like,
Spaghettified, isn't it?
well, that's what happens when you get close to the singularity.
And then like your image freezes, and then it like fades to red
That's
because it's the light that's
that's
trying
no-
to leave.
That's the time dilation.
Right.
Because if you
As you approach the black hole, and you can inject when this gets off. As you approach the black hole, the light. Try to just imagine that you're emitting. It's more anyway. The light from you coming back to the person's eyes is trying to escape the gravity, but as it gets closer and closer, it has to keep climbing and climbing. But then it gets to this point of singularity where it's going the same speed as it's getting sucked, in essence, if you can think of it getting sucked. So it's like an image of the light that was leaving at that moment is stuck to you. The
Well, it
person
seems like
that's
it would just
out.
freeze for everything because you.
Yeah, you do. You freeze, and then slowly that light, it like shifts red as it kind of, I don't know, loses energy or something, and then your image disappears.
well, there's the singularity, and then there would be like the event horizon.
This might be the event horizon.
That would be the event
Yeah,
horizon.
sorry.
So-
I was thinking event horizon the whole time.
The event horizon's where, like,
Light can't escape it. It can't go fast enough to leave how much it's warping.
yes, because like the more massive a planet is or a sun, the faster you need to go to be able to escape its gravitational influence.
Right.
So at some point, an object can become so massive, it's a finite amount of mass you need in a certain volume, that
It can't be escaped.
it can't be escaped.
Because in order for it to be escaped, it would have to move faster than the speed of
An
light.
object
which
would
can't
have to
happen.
move.
Which can't happen.
Which can't happen.
So in the trampoline analogy, if you pulled a point down so steep,
Yep.
if let's say you can throw a marble and it whips around the thing, it eventually escapes. But there's at some point where if you can only throw a marble so fast, if you throw it too deep into that hole, it will not have enough to escape, and then that would be that line of where you can't throw it is singularity.
Yeah, I follow that.
Okay.
So
Well,
light,
the event horizon.
event horizon.
The
sorry,
singularity is that
is the point that you're
infinite
pulling.
depth-
I see. I see.
infinitely dense point.
But have you heard of white holes?
Yes, I have, and those are again something that's theoretically, like, the math says it could happen, but you would need negative mass or something.
I
Like-
don't know.
Negative mass, like say mass that doesn't attract but repels or something, which
What's
the math,
antimatter?
the theory, the math doesn't say you couldn't have it, but we have no evidence to believe that.
So a white hole is a theoretical region of space-time that is the exact opposite of a black hole. Huh.
So instead of pulling everything.
So while a black
pushing it
hole's
out.
gravity is so intense that nothing can escape, a white hole constantly spews out matter, light, and energy, and strictly forbids anything from entering into it.
So it'd be like if you took that trampoline then and flipped it upside down but still had the point, it would be like the negative hell. Everything has to rush
So
away
it's
from it.
Yeah.
it's almost like a magnet a little bit.
It would be, well, it gets weird because I think you technically go to a new universe if you go through that. Like, it's projecting, because there's, like,
A,
if you follow the math, it might not
no,
logically
the math
make
doesn't
sense.
say that it's a new universe.
I think some
That's a
movies would say that.
philosophical interpretation on top of the math. Like, the math, like, just as we don't, like, the math blows up at the black hole singularity,
Mm-hmm.
you could have the math predict the white hole with the singularity in the opposite way, like upside down trampoline, like you said. But you would have to interpret it what happens at that point. Like, the theory of relativity doesn't predict what happens at that point. Like, we don't know what happens.
We have to get a new theory.
You would need a new theory, yeah.
Okay.
So people do. There's such wild ideas in theoretical physics, like, and people have said they could be portals to new universes, or
So
there's a guy that has proposed called the mathematical universe hypothesis or something that says that anything in math is exactly what reality is. So whatever math there is, that's reality actually. It's like
math is reality.
math and reality are the exact same thing. So whatever ideas that you come up with in math, he might say discover.
So yeah, okay. So he would be on the discovered side of things. Math isn't invented; it's discovered.
Would correspond. So
Yeah.
there's wild ideas like that, but you can't test that really. I mean,
Right. Yeah, that's kind of just an outlook on life almost.
Because you're subject to, like, once we find a new theory, then does all of reality change? Like, right now, he's basing reality off of relativity or whatever, but he could have done that with Newtonian physics, like with the whole reality based on Newtonian physics, and
well, this theory would state that any concept you come up with has some correspondence to reality. So
even if it's, like, blatantly wrong, like 1 + 2 is 1.
well, that doesn't follow logically from your
Oh, okay.
system. So but
What's this guy's name? Is he famous?
he's maybe somewhat of a famous Max Tegmark or something.
And he's still,
something
like, he
that.
still exists.
He still is living as far as I know.
Okay.
He still
I
exists.
I don't find the theory at all
So
believable, but that's what I'm just saying. There's wild like
Implications.
philosophical theories of theoretical physics once you get past the actual.
you're saying that Max Tegmark, is that right?
Nice.
All right. So you're saying that future time travel is possible. I mean, we know how to do it, but there's no way that humanity has done it yet. And then past time travel or traveling to the past, it's much more complex. We don't quite know how that would be accomplished, and so like we're nowhere near as close as
But
accomplishing that. Is that kind of what you're saying?
One could argue that there's no way that could ever even consider, like, if it could happen, then there would be people here from the future, right? In theory, right?
Yeah.
So if it can ever happen, then it never will.
So the math predicts that you could have some loop in your space time, which could theoretically get a backwards time travel.
Mm-hmm.
But just because the math says something doesn't mean there's other restrictions or more theory that dictates something. So we don't have any evidence whatsoever that can happen. So like special relativity, general relativity does predict, say, this forward time travel. And there's evidence, like we use it in our satellites and we use it in like certain cancer treatments and stuff.
It's practical in every day. I mean, it's something that scientists are currently using.
Demonstrated, there's lots of experiments that have demonstrated the results. So like the theory does have good predictive power, but just because like those results that are predicted doesn't mean that other results are, and it's just the theory doesn't say which like structures exist. They just say, oh, what could exist. Like it's not mathematically forbidden.
Exist,
yeah.
So it's.
Well, we are nearing our time, and dude, I learned a ton.
Do you have any more things you want to blow our minds with? If you had to think of something we didn't talk about.
Oh, I feel like there's a lot of things that could be said. One short thing, I believe, for any Star Wars fans, maybe you know this, I don't know if it's common. I believe in I don't know if it was one of the sequels or that Yoda, the model of Yoda was partially based on Einstein.
Really?
Wait, look, Bert, that's a Bert question. I can kind of see that.
I just saw a clip last night of George Lucas, the director of Star Wars, saying like, where did Yoda come from? And he said that originally, whenever he was writing the script for the first movie, so A New Hope, Yoda did not exist. He was gonna have Obi-Wan Kenobi be like Luke's mentor, but it just didn't work out, and so he had to kill off Obi-Wan, and then he needed a guy in the second movie to kind of mentor Luke a little bit, and so that's where Yoda came from.
That's funny.
But that is funny because he actually does.
Doesn't that kind of
like
actually
they
look like
resemble
him?
each other? Yeah.
He turned his mustache into his lip.
So is that anti-Semitic?
It's like if you did a LiDAR scan of his face, and that's what it would come up with.
Like
crazy.
part of his hair got kept in.
That's funny. He has like the strangly beard. You know what I mean? That's funny.
Yoda changes so much between the movies. I feel like in the prequels, he like, I don't know. I like when he was a puppet versus when he was probably CGI'd.
Yeah.
Also, can you look up young Einstein? Because
that's the picture you always see.
Well,
that's the picture you always see, and that's when he's old.
Do they even have cameras?
Whoa.
Really, it's a movie
Not
or
that,
something.
but or like look up, that picture right there.
Oh, bro, he used to be good looking.
That's
what he looked like when he released his theories of special and general relativity.
Oh, so bro was a stud.
I think it's just the mustache.
That's like that's what he looked like when he like agreed on listened to the dude with the atomic bomb. That would have been more like what he looked like, the older guy.
Yeah, when he was in the U.S. and
Like Oppenheimer?
Oppenheimer. Yeah.
Okay, so the picture that we always see is whenever he was in the U.S.
When he released his special relativity and general relativity, he would have been like young 20s.
Wow.
Mid 20s maybe.
Right. I mean, that's still insane.
And then
Right, because yeah, we would just look that up. It was 1905 and 1915.
And he was born in 79,
1879.
1879. So he would have been what, like?
Wow, you got that right. 1879.
On Pi Day.
Oh, that's awesome. That's insane.
Wait, they probably just named that Pi Day after.
No,
because that was his birthday.
314.
It's 314, March
Oh,
14th.
okay.
Ooh.
Wait, you didn't know that? That's why it's Pi Day?
I did not know that.
Nah.
I had no idea. That's
Pi
funny.
has a long history.
Pi is freaky.
I think Pi would.
Pi is for another.
I think Pi would be for our second episode. Yeah, whenever you come back on later.
Pi and whatever the E means. Isn't there an E too?
Euler's constant.
Yeah.
Euler was.
I despise both of them. Although I respect Pi.
Euler
I mean,
was
E was.
he has like
He's not
51.
that complicated, is it?
I thought there was one that's like 2 something. Yeah, 2.71.
I always remember the Dr. Shorman was who he did all my math and he loved Euler.
Euler is probably my favorite mathematician.
Really?
Oh really?
He was
Is it Leonard Euler?
Leonard Euler.
Yeah.
He was like had so many areas. Like he is like the most like goated mathematician.
Really?
And I also am biased because he was also definitely a phenomenal Christian from
Awesome.
all like so like way to go. But he like had so many results and like he went blind. He's like Beethoven who went deaf and could play the piano. He went blind and his
Really?
mathematical like output increased. He's like, oh, less distractions. Like
Started using his numbers and.
What? That is crazy.
Wow.
What era did he live? Oh, wait. Oh, it was right there.
like 1700s
18th
maybe.
century. Polymath, widely regarded
When
as
was
one of the
Newton
greatest and most-
compared to him? Do you know?
Probably I don't know.
Like a little before?
Who?
Before
As
or
in
after?
I would've
don't
thought
know.
after.
I thought it was 16th or 17th century.
Yeah, I was gonna say probably
whoa.
before
1642 to 1727.
because calculus was definitely a lot more.
Man,
developed.
that's a long time ago.
I like Galileo too.
Who is the most influential, do you think? Or is there any way to really tell? Like, in your opinion, do you have an opinion who is the most influential out of all?
Mathematician.
Yeah, mathematician. Like, was it Newton or would it be...
Well, depends on what do you mean by influential?
If that person didn't
Archimedes.
exist, what would our view look like today?
Archimedes.
Like, how different would our view look without that person ever existing? You know? Like, I
Well,
have
that's
no
also
idea who it is.
that's
And there's no way to know.
hard
probably.
to say because every mathematician built on the previous mathematicians, except some like. Have you ever heard of Ramanujan?
No.
He was this like
Did he make Roman numerals?
he was this Indian mathematician
Oh,
Like Native American?
whoever made Roman numerals
No,
was
like
on their own.
India.
Oh, okay, Indian.
On their
who
own crack.
like was uneducated and did some like crazy number theory, crazy math, and like I think he said I learned things in dreams and I don't know. But he did some serious math without any like training. So he was one of the few mathematicians that
He did
did a
this
lot
isolated.
he did a lot of results initially isolated.
Wow.
And so some of it was duplicated, but some of it was like crazy, like
Outside of the
series
box.
and results. Yes, that.
I mean,
Oh.
it did say Archimedes was the father of math, but I mean,
Okay. That settles it.
it settles it.
But Euler probably has the most work done and like a billion things named for. He has like all his works probably take up like 20 volumes of material or something. Like
Holy cow.
I don't know.
Okay, we'll go with Euler because he's a Christian.
Yeah.
We'll go with that.
Nice. That's a good answer.
Hey, thanks for coming on.
Yeah, you got
man.
any closing thoughts, or is that...
Thanks for having me.
Yeah, it was good. It was fun. Learned a lot.
Fantastic.
Yep, we'll have to do it again sometime.
Next
Yep.
episode's
Sure.
pie.
Ooh,
Apple.
come hungry to learn.
Oh, we'll be eating on the podcast.
Ooh.
See ya.
All right. See ya.